Now that we've gone over changes in motion, Newton's first law, and Newton's second and third laws, we'll look at some everyday motion and situations where we can apply these forces. Let's define some basic types of forces. First, we have weight. We'll take this situation with a person holding a marble in one hand with a very small mass, and a bowling ball in the other with a very large mass. You can probably tell already that the mass of the objects will depend how much force they exert on the person's hand. Weight is defined as a force that's determined by mass times the magnitude of acceleration due to gravity. This takes the value g, 9.81, or we round to 10 for calculations. A second important force to keep in mind is normal force. We know that when a block rests on a table, gravity is exerting a downward force on the block. However, since the block is at rest, there must be a force of equal magnitude in the opposite direction to keep the block on the table. So we know that this block has its weight, or gravity, pushing downward. Now, we define the upward force of the table that's holding the block up as normal force, or support force. That force helps to balance the force of gravity. Another force that affects most objects is friction. So say you're pushing this heavy box across a table with a rough surface. If you apply a constant force to the box, the second law, F equals ma, suggests that the box will accelerate at a constant rate depending on the force you apply. But it's hard to make the box start moving, and the box stops as soon as you stop applying force. That means there must be some force resisting your pushing. This force is known as friction. Let's take a look at some different types of friction. There are two types of friction. We have static friction and kinetic friction. Static friction is the friction that resists your effort to originally push the box. So you have this box that's standing still on the table, and when you first start pushing, the box is reluctant to move. This is a result of static friction. Now, once you do cause the box to start moving, and it's in motion, kinetic friction still resists your force as the box moves along the table. When we're doing calculations with friction, we also want to keep in mind the coefficient of friction. Friction is proportional to normal force, or objects with greater weight feel a greater force of friction. A coefficient of friction is calculated as the ratio of the frictional force to the normal force. So just as there are two types of friction, there are also two types of coefficients of friction. The coefficient of kinetic friction is, or mu, that's the variable we use, sub k, is kinetic friction divided by normal force. The coefficient of static friction, or mu sub s, is the static friction divided by normal force. Therefore, the force of friction is mu times normal force. Let's do some practice with forces in everyday life. A 10 kilogram dumbbell rests on a stand. We'll draw that in black. What is the force of the stand on the dumbbell? Well, we can start by drawing a free body diagram on the dumbbell. We know that the dumbbell is at rest. We also know that if it weighs 10 kilograms and it's 10 newtons per kilogram, we can say that its weight is 100 newtons. Since the dumbbell is resting on the stand without falling downwards, the stand must be exerting an equal force upwards on the dumbbell. This is equal to the downward force, so the force of the stand on the dumbbell will be 100 newtons. These two forces form an action-reaction pair. Number 2. You push a 4 kilogram book across a table with a force of 20 newtons. The coefficient of kinetic friction is 0.2. So let's start by drawing an FBD for the book. We have the weight of the book, 4 kilograms, so it'll be 40 newtons. We have support force from the table, or normal force. That will also be 40 newtons. We have the force of you pushing the book. This is not to scale, but this is 20 newtons. And then we have the force of friction. We'll call that lowercase f. So let's start by solving for the force of friction. Friction equals mu times normal force. We know that mu is 0.2, and we know that normal force is equal to the weight of the book. So, F equals 0.2 times 40. 0.2 times 40 equals 8. Now we can move on to part 2. What is the magnitude of the book's acceleration? Well, let's solve for the net force acting on the book. if we have 20 in this direction and 8 newtons in this direction, the net force will be 20 newtons minus 8 newtons, or 12 newtons. Now we know F equals ma. We know that F equals 12 newtons. We know that m equals 4 kilograms times a. Now we can divide both sides by 4 to find that a equals 3 meters per second squared. Number 3. A student pulls a box by a rope with a force of 180 newtons at an angle of 25 degrees above the horizontal. The box has a mass of 35 kilograms and the coefficient of friction is 0.27. So let's draw an FBD for the box. We have the weight of the box here. This is 35 kilograms times 10, so that's 350 newtons. We know that there's some normal force pulling up on the box to balance its weight. We also know that there's a frictional force pulling backwards because we are given a coefficient of friction. And we have this force at an angle. It's 25 degrees and it's 180 newtons. That's how much the student is pulling on the box. So let's start by solving for normal force because that'll help us to solve for friction. In other situations where the force of the student pulling on the box is parallel to the horizontal, the normal force would simply be equal to the weight of the object. But in this case, since the student is pulling up slightly on the box, this is compensating for a bit of the box's weight. So let's set up the equation that we did before for free body diagrams, where we set the net force equal to 0. So we'll say net force in the y direction, Fy, equals, we have 180 sine 25 degrees. We have the normal force times the sine of 90 degrees. And we have the weight, 350 newtons, times the sine of 270 degrees. Now let's simplify this a little bit. 180 times the sine of 25 degrees is 76.1. We know that the sine of 90 degrees is just 1, so that's n. And 350 sine 270 will be negative 350. Now let's bring the 350 over and subtract 76.1. We'll get 350 minus 76.1 equals n, or n equals 273.9. That's the normal force. Now we can solve for friction. Friction equals mu times the normal force. So friction equals 0.27 times 273.9. We'll multiply that out, and we find that the force of friction on the box is 73.96 newtons. Now this will allow us to solve for acceleration. Let's look at the direction in which the box is accelerating. We know that these forces are equal to 0 in the y direction because the box is at rest on the table. It's not moving up or down. However, the forces are not balanced in the x direction, or going this way. We know that we have two forces with x components. We have the force of friction pulling back, and we have the x component of this pulling force pulling forward. We'll call that T for tension. So we already know the force of friction. So let's start by solving for this x component of the tension. We have 180, this time it's cosine 25 because it's in the x direction. That equals 163.14. Now we're ready to solve. We can find the net force on the box. F equals 163.14 minus 73.96. This will equal 89.2 newtons. This will equal mass times acceleration. We know that the mass of the box is 35 kilograms. The acceleration we'll call A. Divide both sides by 35. We get that A equals 2.55 meters per second. So now we've gone over all 4 parts of Chapter 4, and I've given you some problems to help you practice. Thanks for watching.